Let's talk about loading data using the DataStax Enterprise Graph Loader. The DataStax Graph Loader is just one of 5 ways you can load data into an existing graph. In this presentation, we'll be covering the Graph Loader in depth, but there are 4 other ways you can load data into DataStax Graph. The Graph API is used when creating small to medium-sized graphs. One can execute individual statements in the Gremlin console or in DataStax Studio, or write a script that uses many statements programmatically. Now, this method is generally slower than Gremlin I/O. However, Gremlin I/O is more suitable when exporting and importing existing graphs. Gremlin mutating traversals are more suitable for mutating existing graphs. Now, the Graph Loader utility is capable of parsing existing collections of text files and datasets stored in JDBC-compatible databases and loading such data as graphs into DataStax Enterprise. This utility is designed for loading small to medium-sized graphs as well. There is a Spark-based bulk loading mechanism that is ideal for large graphs. The DSE Graph Loader is a customizable command line utility that's great for loading small to medium-sized graph datasets. It can load data from a variety of sources, including flat files and database connections through JDBC. It is a Groovy-based tool, so while you can incorporate transformations into your data mappings, this method is deprecated and should not be used. This is an overview of how the DataStax Graph Loader works. First, a user must create a loading script in Groovy. This script tells the Graph Loader about preferred configurations, data sources, and data mappings. The Graph Loader will use the mapper script to read data from the respective data sources and load it into DSE Graph. There are 3 data processing stages that the DataStax Enterprise Graph Loader goes through. First, there's a preparation phase. This is where the Graph Loader will validate the data from the data sources, check to make sure that you have the proper schema in place, and of course, validate the loading script for any possible issues. Then, the Graph Loader will begin loading or retrieving existing vertices and caches them for use in the 3rd step, which is the edge and property loading. The edge and property loading stage is generally the most time-consuming. When loading multi-properties, the schema should reflect that fact to avoid having upserts. Let's talk about the different data sources and file formats you can use with the DataStax Graph Loader. You have support for all the formats you would expect: CSV, JSON, delimited text, and also support for graph-specific formats such as GraphSON, GraphML, and Gryo. What's also interesting is that the DataStax Graph Loader can load data directly from JDBC-compatible databases, and this includes other graph databases such as Titan, Janus, and Neo4j. Next, we're going to be discussing loading script design for the DSE Graph Loader. As we talked about previously, the loading script defines the Graph Loader configuration, it defines the data sources, and defines the data mappings. And because it is a Groovy-based tool, it also supports Groovy-based transformations, though this functionality is deprecated. Here are some of the configurations that you can define with the DataStax Graph Loader. The options address and graph are straightforward and required. Create graph enables the creation of a new graph by default. And if you want the best performance, you should be loading data into an existing graph with well-defined schema that has indices to support useful lookups during data loading. Therefore, create schema should be set to false. Another performance-related optimization is possible with load new equals true. If you're loading a new dataset, DataStax Graph Loader will rely on this option and will not waste time verifying if a vertex or edge already exists in the graph. It will assume to-be-imported graph elements are new and have unique IDs. There's also a finer-grained mechanism to specify existence of specific graph elements when defining a data mapping. We'll cover this later in the presentation. There are many other options for customization, so please take a look at the documentation for an expansive list. Here are a few parameters you can adjust for increasing or decreasing performance. Read threads is the number of threads used to read data from the data input. Load vertex threads is the number of threads used for loading vertices. By default, it's set to 0, which will force the number to be the number of physical cores divided by 2. Load edge threads controls the number of threads used for loading edges and properties and will default to 0, which translates to the number of nodes in a respective data center times 6. Now that we know some of the important configurations for the DataStax Graph Loader, let's put them to good use. Here's how you would define configurations within your loading script. Notice the config declaration followed by the parameter and the value. You can also see an alternate syntax at the bottom using a comma to separate parameters on a single line. Once we have our configurations defined, it's time to define our input sources. You can see that from the file method, we can specify which type of file format we're loading and whether or not there's a specific delimiter or header associated with it. Now, if your input data is one of 3 main graph file formats, the syntax is a little bit different. We call the graph method specifically the file name and then the type of graph format we're reading from. Lastly, here's how we can load data from a JDBC-compatible database. You first need to create a database connection, which we can do by calling the database method, provide a connection string, database type, and then of course the authentication. Then we can use that database connection to query for our data in SQL format. Once we have our inputs defined, we can then use the transformation API. Please note that this will be deprecated and might be replaced with a different API in the future. The main methods you have access to are the map, flat map, and filter transformations. Each will create a new dataset that's formed by applying a function on each element of the input dataset. With a map, there's a one-to-one correspondence between input and output elements. With a flat map, there's a one-to-many correspondence. As you would expect with filter, the new dataset is formed by the elements in the input dataset that return true with the function f. Here's an example on how to create transformations in your loading script. As you can see, we define our input, then filter on it to keep users who are over the age of 21. Then we use the map method to add a U in front of the user ID value. So for example, 25 would now become U25. In this example, flat map adds M in front of the movie ID. For example, 44 becomes M44. Next, it splits the genres literal into the list of genres and modifies each element of the list to be a map with fields, movie ID, and genre. This returns a new belongs to dataset created by expanding lists returned by the lambda function. This new dataset can later be mapped to edges in a graph. This is how you map input data to graph constituents. Simply put, you call the load method, which takes input data and specify whether you're loading vertices or edges. The as vertices or as edges method takes a mapper input, which we'll discuss next. Now, before we create our mappings, let's get introduced to the mapping API. Each vertex or edge must have a label, use label, or label field. A key is what uniquely identifies a graph element. It's not necessarily a vertex or edge ID. Vertex property and property can map fields to properties. They do not need to be used explicitly if a field and property names are the same, because any data field becomes a vertex or edge property by default. Similarly, value may not need to be used explicitly. Use ignore to not create properties out of fields by default. IsNew and exists allow for finer-grained mechanisms to specify existence of specific graph elements when defining a data mapping. They override the behavior specified by the load new configuration option. InV and OutV help define neighbors of a vertex. InE and OutE help define incident edges of a vertex. InV and OutV, with different signatures, help define endpoints of an edge. There are more methods, so please consult the documentation for more information. Now, let's put what we just learned to good use. Here's an example of mapping our person data to vertices. Since we're loading vertices, we use the asVertices method to begin to map our data. The label of this vertex is person, and the key within the input data is person ID. Both examples here are valid. They just use slightly different syntax. Here's an example of mapping actors to edges. This mapping is a little more in depth because we need to tell the graph loader which adjacent vertices to create an edge between. Because we're loading new edges to existing vertices, we can call the exist method to our vertex mappings. Again, this is for optimization. Both examples do the same thing with different syntax, and both are valid. Now that we've learned how to create our own loading script, it's time to learn how to actually run the graph loader. All you need to do is run the graph loader utility, specify your loading script, and any additional configuration. It's also worth noting that the command line options can be overridden by the loading script options. Make sure that you're using the DataStax Graph Loader that matches with your DataStax Enterprise version. It's time to put your new Graph Loader knowledge to use with this hands-on exercise.